Okay, today we're going to look at our last section in the polar unit, which is a polar form of complex numbers. So first thing we're going to look at is plotting complex numbers on the complex plane. Now the complex plane is very similar to the rectangular plane, except that the horizontal axis is the real axis and the vertical axis is the imaginary axis, labeled IM and RE. So the horizontal axis is the real axis, so you label the real part of the complex number on the real axis, and then the vertical axis is the imaginary part, imaginary axis or the imaginary part. So if you had the complex number 3 plus I, 3 is considered the real part, and one I is considered the imaginary part. So to graph this, I would go right 3 on the real axis, and then up 1 on the imaginary axis to make our dot. That would be Z1. For example, if I had Z2 is equal to negative 2 plus 3I, to graph this, I would go left 2 and up 3 to plot my Z2. Okay, I want you to try plotting Z3, which is negative 1 minus 2I. So that would be left 1, down 2. And then a Z to the 4th, which is 4 minus 5I. Try plotting it. That would be right 4, down 5. And that'll be our Z to the 4th, Z4. Okay, now we know how to plot this. Next thing we're going to learn is something called the absolute value of a complex number. By definition, absolute value of a complex number is the distance between the origin and the point A, comma B. Okay, the absolute value of the complex number Z equals A plus BI. Notation, the absolute value of A plus BI is equal to, well, that distance, using our Pythagorean theorem, would be the square root of A squared plus B squared. So let's see, if I chose one of these points, so let's say I looked at Z2, and I want to find the absolute value of Z2. Graphically, what this would represent is that it's the distance from the origin to the point. So it's the distance of this line segment. And so I can use Pythagorean theorem, and we can do the absolute value of Z2 is equal to the square root of 2 squared plus 3 squared, or 4 plus 9, or the square root of 13. Would be the absolute value of Z squared. All right, so here is another example. We're going to do this algebraically. I want to find the absolute value of negative 2 plus 5I. So that's going to be equal to the square root of negative 2 squared plus 5 squared. And that gives us 4 plus 25, which is 29. So our answer, absolute value of this number is square root of 29. Your turn. Find the absolute value of 3 minus 4i. Okay, so that's equal to the square root of 3 squared plus 4 squared, which is the square root of 25, which equals 5. Okay, next thing I want to learn is how to convert between a complex number into what's called the polar form of the complex number. Sometimes this polar form is called the trigonometric form of complex numbers. So it's sometimes called polar form or trigonometric form of complex numbers. Okay, so again, the polar form of a complex number is Z is equal to R times cosine of theta plus I sine of theta, where A is defined by R cosine theta, and B is defined by R sine theta. And that should be very, very familiar. Sort of like, remember on our last section, X was defined by R cosine theta, and Y was defined by R sine theta. Now A is defined by R cosine theta, and B is R sine theta. And then to get that standard form that we just recognize here, notice I just factor out my R, the GCF of the R, and that gives us that form that I wrote Z in earlier. You also will need to find the R value. To find R, that is just simply equal to, it's that radius when it's graphed on the plane. So it's the absolute value. So it's just radius is equal to the square root of A squared plus B squared. And you'll also need to find theta, and we're going to use theta is tangent of theta is equal to B over A, just like previous tangent of theta was equal to Y over X. So notice these formulas are very similar to ones we've already used. The number R has a special name. It's called the modulus of Z, and the angle theta has a special name. It's called the argument of Z. So your first step when you're converting a complex number into trigonometric form is to find the modulus and to find the argument of the number. So let's do that. Looking at this example, z is equal to negative 2 minus 2 the square root of 3i. We need to figure out r. R is equal to the square root of a squared. In this case, a squared is negative 2. And b squared, which is negative 2 the square root of 3. All right, so 2 squared is 4. Negative 2 squared is 4. Square root of 3 squared is 3. 4 times 3 is 12. So this gives us 4 plus 12. Or the square root of 16, which is simply 4. Okay, so we know our modulus is 4. Now, its next step is we need to figure out our argument. But before we figure out our argument, we have to identify the quadrant that this point z is in. So all you do is simply do a quick sketch of the complex number on the complex plane of z. So z is negative 2 minus 2 the square root of 3. So I'd go left 2 and down to the square root of 3. And so that puts us in quadrant 3. So to find the argument, we're going to set up the equation that tangent of theta is equal to b over a. So tangent of theta will be negative 2 the square root of 3 over negative 2. Which simplifies down to tangent of theta is equal to the square root of 3. So I need the angle whose tangent is square root of 3. So I'm going to find the reference angle first because remember tangent or arctangent only gives us in quadrants 1 and 4. And so to make it a quadrant 3, I need to take pi plus that reference angle. And I figured out that my theta in this problem is 4 pi over 3. So I've now found my r and my theta. So I can replace my z as r, which is 4, times cosine of theta, which is 4 pi over 3, plus I times sine of 4 pi over 3. I have now converted this complex number into polar form. Okay, now it's your turn. Try z is equal to 6 minus 6i. Convert that into trigonometric or polar form. Recall, first we have to find our modulus. So r is going to be equal to the square root of 6 squared plus negative 6 squared, which is 36 plus 36, which is r is equal to square root of 72. Simplifying that down, r is equal to 6 the square root of 2. Okay, we need to figure out which quadrant this is in. And so if I plot the point 6, negative 6i, I end up in quadrant 4. Okay, so I need to find my argument. So tangent of theta is equal to negative 6 over 6, or tangent of theta is equal to negative 1. So the angle whose tangent is negative 1 will give us that pi over 4, actually negative pi over 4. But 2 pi minus pi over 4 ends up that we are in quadrant, for quadrant 4, that'd be 7 pi over 4. So therefore, z is equal to 6 the square root of 2 times the cosine of 7 pi over 4 plus I sine of 7 pi over 4. And you successfully converted this complex number into trigonometric form. Okay, let's go the other direction. Now I have the equation in polar form, and I want to convert it into standard form of the complex number. So just like before, we need to identify a few specific things. So we need to find a and b this time. Well, we know that our cosine of negative pi over 3, so cosine of negative pi over 3 we can figure out to be 1/2. And we know that the sine of negative pi over 3 from the unit circle is equal to negative square root of 3 over 2. So I could substitute in place of cosine of negative pi over 3, 1/2. In place of sine negative pi over 3, I can substitute in square root of 3 over 2i. Okay. Now I can distribute the square root of 8 to each term to get rid of the parentheses. And then I can simplify. Square root of 8 is the same as 2 the square root of 2. And square root of 24 is the same as 2 the square root of 6. And then I can simplify each of those expressions down, and I get that z is equal to square root of 2 minus the square root of 6i. So it's much faster to go in this direction. Okay, I want you to try the next example. Okay, to convert this polar form into standard form, first thing I need to do is evaluate cosine of 2 pi over 3, which is negative 1/2, and sine of 2 pi over 3, which is square root of 3 over 2. Then I replace cosine of 2 pi over 3 with negative 1/2, and the sine of 2 pi over 3 with square root of 3 over 2. Distribute the 8 to get rid of the parentheses. I get negative 4 plus, and if I simplify that down, that would be negative 4 plus 4i. 4 to the square root of 3i. Sorry, I forgot my square root of 3. So your correct answer is z is equal to negative 4 plus 4 to the square root of 3i. Now we know how to convert in between the forms. Let's learn how to multiply and divide complex numbers written in trigonometric form. So the rule is to multiply two complex numbers together that are written in trigonometric form. You multiply the radii together, so r1 times r2, and then you add the angles inside the trig function. So that would be r1 times r2, all multiplied by cosine of theta 1 plus theta 2, plus I sine of theta 1 plus theta 2. Now, to divide, you're going to do the opposite operations. So you're going to divide your r1 and your r2, and you're going to subtract your angles inside the trig function. So we're going to do cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. And that's it. That's how you multiply and divide trigonometric functions. Now, because of the division here, we know that z2 cannot equal 0, because then r2 would be 0. We cannot have division by 0. All right, so let's try one. I want to find the product of these two trigonometric form complex numbers. And so I take 3 times 2, multiply my r's, and then I'll have cosine of pi over 4 plus 3 pi over 4 plus I times sine of the product of the sum of those two angles, which is pi over 4 plus 3 pi over 4. All right, 3 times 2 is 6. Pi over 4 plus 3 pi over 4, it gives us 4 pi over 4, which simplifies down to pi. And then we simplify even farther. I know cosine of pi is equivalent to negative 1, and sine of pi is 0. And so this actually simplifies down to the real number negative 6. All right. You try the next example. Okay, we're going to find z1 times z2. That's going to be 2 times 8 times by the cosine of 2 pi over 3 plus 11 pi over 6 plus I times sine of 2 pi over 3 plus 11 pi over 6. All right, we know 2 times 8 is 16, and we know 2 pi over 3 plus 11 pi over 3 simplifies down to 5 pi over 2 plus I sine of 5 pi over 2. Now, the reference angle for 5 pi over 2, if I go, because that's just multiple times around the unit circle, I find that that reference angle is simply pi over 2, and we know the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So we end up with 16i as our answer here. This time I did with degrees. We can use radians or degrees in these angles. Okay, so divide, we divide our radii, so that'd be 24 divided by 8 times by cosine of 300 minus 75 degrees plus I times sine of 300 minus 75 degrees. All right, 24 divided by 8 is 3. 300 minus 75 is 225. For the unit circle, I know that the cosine of 225 degrees is negative square root of 2 over 2, and the sine of 225 degrees is also negative square root of 2 over 2. So distributing that 3, I get a negative 3 the square root of 2 over 2 minus 3 the square root of 2 over 2i as my answer. Okay, what if I want to take a complex number and raise it to powers? To do this, we use what's called de Moivre's theorem. De Moivre's theorem simply says that if you have a complex number written in polar form and you want to raise it to a n power, as long as n is a positive integer, then z to the n is equal to r to the n times cosine of n times theta plus I times sine of n times theta. So here's an example. I'm going to find the complex number here. Now, the key is to use de Moivre's theorem is it has to be written into polar form. So that's going to be my first step. So I'm going to practice this. I'm going to pause and let you do that. Remember, in order to convert to polar form, we first have to find our modulus and our argument. So we'll find our modulus. That's a squared plus b squared. In this case, that's going to be 2. Then we're going to find our argument. So we're going to quickly plot this and figure out which quadrant we are in. And we know that tangent of theta needs to be equal to square root of 3 over negative 1, or tangent of theta needs to be equal to negative square root of 3. We are in quadrant 2. So the angle whose tangent is negative square root of 3 in quadrant 2 is, well, the reference angle is pi over 3, and so for quadrant 2, I take pi minus pi over 3, which gives us 2 pi over 3. Or you could have just known that for your unit circle. So that's theta. So our polar form of this complex number, therefore, would be 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3. Okay, so now I have my complex number written in polar form. I can use the Moivre's theorem to find z to the 12th. And so that's going to be equal to our radius, which is 2 to the 12th, times by cosine of 12 times our angle of 2 pi over 3, plus I times sine of 12 times 2 pi over 3. Now 2 pi over 3 is equal to 8 pi, and 2 to the 12th is equal to 4,096. And then finally, we know cosine of 8 pi is the same as equal to simply 1, because it's the same as a cosine of 2 pi. And we know sine is equal to 0 of 8 pi. Sine of 8 pi is equal to 0. And so our answer is simply the number 4,096 is what z to the 12th power is equal to. Now I raised something to the nth power, so now let's go in the opposite direction. What if I want to find the nth root of something? Now nth roots, these nth roots can also be thinking of the roots of a polynomial, kind of do that relationship. Now remember, we've learned previously in college algebra, fundamental theorem of algebra, is that a polynomial equation has degree n has n roots. So for a positive integer n, a complex number z equals r cosine theta plus I sine theta has exactly n distinct nth roots. So z of k, which is represented the kth root of this problem, is found by taking the nth root of r times by the cosine of theta plus 2 pi k over n plus sine plus I sine of the same angle, which is theta plus 2 pi k over n. Okay, n is the k is just integer 1, 2, 0, 1, 2, 3, etc. as we go around the unit circle. We'll start with 0 times around the unit circle, and then 1 time, then 2 times, etc. And n is the number of roots. Now we will repeat this to find all the roots until we get to n is equal n minus 1. So 1 less than the number of roots we're looking for. So let me see how this would work out. For example, I want to find all 6 roots of 1. So first off, I have to get the number 1 converted into polar form. So if I wrote that in complex form, standard form, that would be 1 plus 0i. And then I find my modulus, which is r is equal to a squared plus b squared. So in this case, it's just square root of 1, which is 1. Then I need to find my argument, which is tangent of theta is going to be equal to 0 over 1, or tangent of theta equals 0. And that would be 0 radians. So my polar form of this number is z is equal to 1 times cosine of 0 radians plus I times sine of 0 radians. And we want to find all 6 roots. So in this case, n is going to be equal to 6. Okay, z to the k is going to be the sixth root of 1 times cosine of 0 plus 2 pi k over 6 plus I sine of 0 plus 2 pi k over 6. So in k is equal to 0, the sixth root of 1 is just 1. And that becomes cosine of 0 plus 0, so it's 0 over 6, which is just 0. So we end up with z sub 0 is 1 plus cosine of 0 plus I sine of 0. Cosine of 0 is equal to 1, and sine of 0 is equal to 0, so I get the number 1. Now z1, this time k is 1, so the sixth root of 1, which is same as 1, is the cosine of 0 plus 2 pi, which is just 2 pi, over 6. And 2 pi over 6 simplifies down to simply pi over 3. So cosine of pi over 3 we know is equal to 1/2. And plus I, the sine of pi over 3, which is square root of 3 over 2. And so our answer for Z1, our next root, is 1/2 plus square root of 3 over 2i. Our second root, this time k is 2, so that gives us 4 pi over 6. 4 pi over 6 simplifies down to 2 pi over 3. And cosine of 2 pi over 3 we know to be negative 1/2. And the sine of 2 pi over 3 is the square root of 3 over 2 times I. Z to the third, this time k is 3, so that's going to give us 6 pi over 6, which simplifies down to pi, plus I sine of 6 pi over 6, or pi. We know that cosine of pi is negative 1, and sine of pi is 0, so that gives us the number negative 1. Z to the fourth, 6th root of 1 is still 1. Cosine, this time 6 times 2 is 12, so 12 pi over 3. 12 pi over 6, which simplifies down to 4 pi over 3. We know that the cosine of 4 pi over 3 is negative 1/2, and the sine of 4 pi over 3 is negative square root of 3 over 2 times the I, of course, and that is our fourth root answer, or Z to the fourth answer. Now Z to the fifth, which is our sixth and last root. This time 5 times 2 pi gives us 10 pi over 6, which simplifies down to 5 pi over 3. We know the cosine of 5 pi over 3 is equal to 1/2, and we know that the sine of 5 pi over 3 is negative the square root of 3 over 2. So our Z5 is, or so our last root would be 1/2 minus the square root of 3 over 2i. And you found the 6 roots of this number. Okay, now I want you to try this next example. Given that z is equal to negative 2 plus 2i, I want you to find the 3 cube roots of z. Step 1 is convert that z into polar form. So we need to find our modulus. To find our modulus, we just take negative 2 squared plus 2 squared and take the square root of that, which gives us 2 the square root of 2. Just for simplifying purposes, I'm going to leave it as the square root of 8 for now. And I'll show you why in a moment. Theta is in quadrant 2. So to find theta, I take tangent of theta is equal to 2 over negative 2, which is tangent of theta is equal to negative 1. The angle whose tangent is negative 1. I'm going to do degrees this time. Is 135 degrees, is 45 degrees. So if we get into our reference angle in quadrant 2, that makes it 135 degrees. All right, so my polar form or trigonometric form of this complex number will therefore be this z is equal to the square root of 8 times the cosine of 135 degrees plus I sine of 135 degrees. And we want to find the cube root, the 3 cube roots. So we want to find where n is equal to 3. So using our formula, that z to the k would therefore, if n is equal to 3, would be the third root of the square root of 8 times by the cosine of theta, which is 135 degrees, plus 360k over 3, plus I sine of 135 degrees plus 360k divided by 3. All right, so let's figure out what the cube root of the square root of 8 is. So I'm going to do this by converting these to fraction power. So remember that the square root can be written as 1/2 and the cube root would be written as 1/3. When you take a power of a power, you multiply your exponents together to get 1/6. Then I know that 8 is the same as 2 cubed. So I can rewrite this, a power of a power therefore is 2 to the 1/2. So the cube root of the square root of 8 simplifies down to simply the square root of 2. And so my r is the square root of 2. Now to find z of 0, k is now 0. So that's going to be 135 degrees divided by 3. 135 degrees divided by 3 is just the square root, is just 45 degrees. And so we know that the cosine of 45 degrees is equal to the square root of 2 over 2. And the sine of 45 degrees is also square root of 2 over 2. Now when I take the square root of 2 times the square root of 2 over 2, that becomes 2 over 2, which is 1, plus I. So our z of sub 0 is 1 plus I. Z sub 1 is the square root of 2 times the cosine, but this time 135 degrees plus 360 divided by 3. And when I do that, I end up with 165 degrees plus I sine of 165 degrees. Now, this is the first time we had one that is not on our unit circle. So when you get an angle here that's not on the unit circle, all you do is type this into your calculator, make sure you're in degree mode, and we'll just write our decimals. We usually do 4 decimal places. So I'm going to take the square root of 2 and times it by cosine of 165 degrees. And I get negative 1.3660. Doing the same thing with the sine, I end up with 0.3660I. All right, our last root, z sub 2, is equal to square root of 2 times cosine. This time k is 2, so that's 135 degrees plus 720 divided by 3, which is 285 degrees. That's also an angle that's not on the unit circle, and so I'm going to use my calculator, and I end up that my answer is 0.3660 minus 1.3660I, rounded to 4 decimal places. And now we found the 3 cube roots of this function using our nth root theorem.